Chapter 1 Introduction to Weight Shift Control. Introduction. Weight Shift Control (WSC) aircraft means a powered aircraft with a framed pivoting wing and a fuselage controllable only in pitch and roll by the pilot's ability to change the aircraft's center of gravity (CG) with respect to the wing. Flight control of the aircraft depends on the wing's ability to deform exibly rather than on the use of control surfaces. This chapter provides background on the development of the WSC aircraft, its unique characteristics, the requirements for obtaining a WSC license, Airman Certificate, aeronautical decision-making, ADM, and the unique medical factors required to operate WSC aircraft safely. Further, it is highly recommended that all pilots develop a general understanding of aviation by becoming familiar with the Pilot's Handbook of Aeronautical Knowledge and the Aeronautical Information Manual, AIM. Listings of other available handbooks can be found on the Federal Aviation Administration, FAA, website at www.faa.gov. History. From the beginning of mankind, we have looked to the skies where legends and myths have entertained and provided us the dream to fly. Through the Middle Ages, the idea of flight evolved across Europe, with Leonardo da Vinci well known for designing ying machines to carry humans. In 1874, Otto Lilienthal, a German mechanical engineer, started designing, building, and flying bird-like wings. Figure 1.1, he published his work in 1889, and by 1891 made flights of over 100 feet in distance. Otto was the faa-h-8083-5 successful hang glider pilot to design, build, and fly a number of wing designs. Figure 1.2, in 1903, the Wright brothers' gliders became powered and the airplane was born as the Wright Flyer. In the early 1900s, aircraft configurations evolved as faster speeds and heavier loads were placed on aircraft in flight. As a result of the new demands, the simple flexible wing was no longer sufficient and aircraft designers began to incorporate rigid wings with mechanical aerodynamic controls. These new ideas in wing design eventually resulted in the familiar aileron and rudder configurations found on the modern airplane. Commercial applications were driving the need for faster and heavier aircraft. However, the dream of achieving man-powered flight in its most bird-like form was evolving along a different path. As rigid wing design enjoyed development for military and commercial applications, the flexible wing concept lay largely dormant for decades. In 1948, a flexible wing design was created by Francis Melvin Rogallo as a ying toy kit for which he obtained a patent in 1951. Figure 1.3, Rogallo's design concept evolved down two parallel paths in the early 1960s, military and sport flight. The military application was the National Aeronautics and Space Administration, NASA, development of the Rogallo wing into the Parazev, paraglider research vehicle later renamed the Paroing. That aircraft had rigid leading edges shown in Figure 1.4. NASA had the cart attached to the keel hanging below the wing and using weight shift to control the wing in the same fashion as modern WSC aircraft today. During this same period, other pioneering engineers and enthusiasts started developing the Rogallo wing for sport. One was aeronautical engineer Barry Palmer, who saw pictures of the NASA wings and, in 1961, constructed and flew a number of hang gliders based on the Rogallo design. Figure 1.5, his efforts and others evolved to the WSC aircraft in the late 1960s. Another pioneer was John Dickinson of Australia, who used the NASA Rogallo wing design but incorporated a triangular control bar that provided structure for the wing during flight with ying wires. Figure 1.6. Hang glider. The WSC system and the good ying qualities of the Rogallo wing and Dickinson wing, combined with its easy setup and portability, started the hang gliding craze in the early 1970s. Figure 1.7, in 1967, the faa-h-8083-5 powered aircraft based on the flexible wing concept of Dr. Rogallo was registered as amateur-built experimental. Flexible wing development continued, and by the early 1970s several adventurous entrepreneurs were manufacturing Rogallo wings for sport use. Another significant step in wing design was an airfoil that would change shape for optimum performance at slow and fast speeds. It was the faa-h-8083 Rogallo wing with a lower surface that could enclose the structure that holds the wings out. Enclosing this crossbar tube and providing a thicker airfoil similar to the airplane wing provided a jump in high-speed performance. This double-surface wing was quickly adopted by manufacturers as the high-performance standard and is used on faster WSC aircraft today. Figure 1.8, activity in the hang gliding community increased throughout the 1970s, which resulted in the proliferation and development of stable, high-quality modern hang gliders like the one shown in Figure 1.9. Motorized hang gliders. In the late 1970s, performance had increased enough to allow motors to be added to hang gliders and FL-on practically. It was not until the wings had become efficient and the engines and propeller systems evolved that the faa-h-8083-5 commercial motor for a hang glider was introduced in 1977, the Soarmaster. It used a two-stroke engine with a reduction system, clutch, and long drive shaft that bolted to the wing frame. It had a climb rate as high as 200 feet per minute, FPM, which was acceptable for practical ight. However, during takeoff the wing would overtake the running pilot, and launching was very difficult. Also, while ying, if the pilot went weightless or stalled under power, the glider would shoot forward and nose down into a dive. Overall, with the propeller pushing the wing forward during takeoffs and in some situations while ying, this was unsafe for a wide application. Figure 110, a maturing industry. Engines and airframe technology had made great advances because the ultralight faa-crossed wing evolution was providing lighter weight, higher power, and more reliable propulsion systems. The propeller was moved lower for better takeoff and FL-light characteristics, wheels were added, and the trike was born at the end of the 1970s. A trike describes a Rogallo-type wing with a three-wheeled carriage underneath, much like a tricycle arrangement with one wheel in front and two in back. Trike is the industry term to describe both ultralight vehicles and light sport aircraft, LSA, WSC aircraft. Figure 111, the major trike manufacturers were formed in the early 1980s and continue to deliver trikes worldwide today. New challenges by the 1980s, individuals were rapidly developing and operating small-powered trikes. This development failed to address the sport nature and unique challenges these new aircraft presented to the aviation community. In an attempt to include these ying machines in its regulatory framework, the FAA issued Title 14 of the Code of Federal Regulations, 14 CFR, Part 103, Ultralight Vehicles, in 1982. Aircraft falling within the ultralight vehicle specifications are lightweight, less than 254 pounds if powered, or 155 pounds if unpowered, are intended for manned operation. By a single occupant, have a fuel capacity of 5 gallons or less, a maximum calibrated airspeed of not more than 55 knots, and a maximum stall speed of not more than 24 knots. Ultralight vehicles do not require pilot licensing, medical certification, or aircraft registration. Ultralight vehicles are defined in more detail with their operating limitations in 14 CFR Part 103. Because training was so important for the single-place ultralight vehicle pilots, the FAA granted an exemption that allowed the use of two-seat ultralight vehicles for training, and the sport of two-seat ultralight training vehicles grew. Throughout the 1990s, worldwide sales of both single-seat and two-seat ultralight vehicles soared, but it was the proliferation of two-seat trainers that took the industry and the regulators by surprise. Worldwide sales of two-seat ultralight vehicle trainers vastly outnumbered the sales of single-seat ultralight vehicles, and it became clear that the two-seat trainers, which were intended to be operated as trainers only, were being used for sport and recreational purposes. This created a demand for increased comfort and reliability, which resulted in heavier, more sophisticated machines. Light sport aircraft, LSA, to address the evolution of the ultralight vehicle and its community of sport users, the FAA issued new rules on September 1, 2004. These rules created a new category of LSA and a new classification of FAA pilot certification to FLY LSA, called Sport Pilot. Additional guidelines established by the FAA can be found in 14 CFR Part 61. Figure 112, this handbook focuses on the WSC aircraft. Aircraft certificated as LSA exceed the limitations defined for ultralight vehicles and require that the pilot possess, at a minimum, a Sport Pilot certificate. The Sport Pilot rule defines the limitations and privileges for both the Sport Pilot and the LSA. In addition, the regulations governing the Sport Pilot rule define the training requirements of prospective sport pilots and the airworthiness requirements for their machines. For instance, an ultralight vehicle must not exceed 254 pounds or carry more than one person. Aircraft that carry more than one person and weigh over 254 pounds but less than 1,320 pounds may be certified as LSA provided they meet specific certification requirements. Therefore, many WSC ultralight vehicles became LSA, provided they were properly inspected and issued an airworthiness certificate by the FAA. Weight shift control aircraft WSC aircraft are single and two-place trikes that do not meet the criteria of an ultralight vehicle but do meet the criteria of LSA. The definition for WSC can be found in 14 CFR Part 1. Flight control of the aircraft depends on the wing's ability to exibly deform rather than on the use of control surfaces. The common acronyms for this LSA are WSC, Weight Shift Control, WSCL, WSC Land, which can be wheels or ski equipped, and WSCS, WSCC, for water operations. A LSA WSC used for sport and private pilot Ying must be registered with a FAAN number, have an airworthiness certificate, a pilot's operating handbook, POH, and/or limitations with a weight and loading document aboard. The aircraft must be maintained properly by the aircraft owner or other qualified personnel and have the aircraft logbooks available for inspection. Dual ight controls are required in two-seat aircraft used for training. The carriage is comprised of the engine and ight deck attached by a structure to wheels, floats, or skis. It may also be referred to as the fuselage. The wing is the sail, structure that supports the sail, battens, ribs, that form the airfoil, and associated hardware. Figure 113, there are several unique features of the WSC aircraft. The wing structure is in the pilot's hands and is used to control the aircraft. There are no mechanical devices between the pilot and the wing. The pilot can directly feel the atmosphere while ying through it because the pilot is holding the wing. This is a direct connection between the wing and the pilot like no other aircraft. The pilot can feel the wing as the wingtips or nose moves up and down, but the carriage and passenger are more stable. Turbulence is not felt as much as in a faa-crossed wing aircraft. Different wings can be put on a single carriage. This allows the pilot to have a large wing that can take off in short distances, which would be good for low and slow ying. A large wing with a lightweight carriage can also be used for soaring and is capable of ying at speeds below 30 miles per hour, mile per hour. At the other extreme, a smaller high-performance wing can be used for ying long distances at high speeds. With a small wing and a larger motor, WSC aircraft can fly at speeds up to 100 miles per hour. The wing can be taken off the carriage and folded up into a tube that can be easily transported and stored. This allows owners to store the WSC aircraft in a trailer or garage, transport the WSC aircraft to a local site, and set it up anywhere. Figure 114. Since the WSC aircraft is designed without the weight and drag of a tail, the performance is significantly increased. The aircraft can take off and land in short fields, has good climb rates, can handle a large payload, has a good glide ratio, and is fuel efficient. The WSC LSA typically can carry 600 pounds of people, fuel, and baggage. Besides having large and small wings for different speeds, the WSC aircraft wings can have wires for bracing, struts, or a combination of both. Throughout this handbook, both are used in diagrams and pictures. WSC aircraft are typically on wheels, but there are models that can land and take off on water and snow. Figure 115, Weight Shift Control LSA Requirements. A WSC LSA must meet the following requirements. 1. A maximum takeoff weight of not more than 1,320 pounds, 600 kilograms, for an aircraft not intended for operation on water, or 1,430 pounds, 650 kilograms, for an aircraft intended for operation on water. 2. A maximum airspeed and level light with maximum continuous power (VH) of not more than 120 knots calibrated, computed, airspeed, CAS, under standard atmospheric conditions at sea level. 3. A maximum stalling speed or minimum steady light speed without the use of lift-enhancing devices, VS1, of not more than 45 knots CAS at the aircraft's maximum certified catted takeoff weight and most critical center of gravity. 4. A maximum seating capacity of no more than 2 persons, including the pilot. 5. A single reciprocating engine. 6. A faa-crossed or ground-adjustable propeller. 7. Fixed landing gear, except for an aircraft intended for operation on water. 8. Fixed or retractable landing gear, or a hull, for an aircraft intended for operation on water. Flight operations and pilot certificates. The FAA is empowered by the United States Congress to promote aviation safety by prescribing safety standards for civil aviation programs and pilots. Title 14 of the Code of Federal Regulations, 14 CFR, formerly referred to as Federal Aviation Regulations, FAR, is one of the primary means of conveying these safety standards. Figure 116, 14 CFR Part 61 specifies the requirements to earn a pilot certificate and obtain additional WSC privileges if already a pilot. 14 CFR Part 91 is general operating and flight rules for pilots. The Aeronautical Information Manual, AIM, provides basic flight information and operation procedures for pilots to operate in the National Airspace System, NAS. Basic Pilot Eligibility. Title 14 CFR, Part 61 specifies the requirements to earn a pilot certificate. This regulation also states the pilot applicant must be able to read, speak, write, and understand the English language. The FAA Practical Test Standards, PTS, establish the standards for the knowledge and skills necessary for the issuance of a pilot certificate. It is important to reference both of these documents to understand the knowledge, skills, and experience required to obtain a pilot certificate to FLY a WSC aircraft. Figure 117. Pilot applicants and students Ying solo must have a valid driver's license or a current third-class medical certificate issued under 14 CFR Part 67. In addition to a valid driver's license or a medical certificate, each pilot must determine before each FLite that he or she is medically fit to operate the aircraft in a safe manner. If using a valid driver's license to exercise the privileges of a sport pilot certificate, then all restrictions on that driver's license are also upheld. A current FAA third-class medical certificate must be obtained to exercise the privileges of a WSC private pilot certificate. Existing pilots, including previous student pilots, who have had their FAA medical certificate or most recent application denied, revoked, withdrawn, or suspended by the FAA, are not allowed to operate using a driver's license until the denial on the airman record is cleared by having a valid third-class medical certificate issued. Flight safety practices. In the interest of safety and good habit pattern formation, there are certain basic FLite safety practices and procedures that must be emphasized by the FLite instructor and adhered to by both instructor and student, beginning with the very faa-h-8083-5 dual instruction FLite. These include, but are not limited to, collision avoidance procedures including proper scanning techniques and clearing procedures, runway incursion avoidance, and positive transfer of controls. Collision avoidance. All pilots must be alert to the potential for mid-air collision and near mid-air collisions. The general operating and FLite rules in 14 CFR Part 91 set forth the concept of see and avoid. This concept requires that vigilance shall be maintained at all times by each person operating an aircraft. Most mid-air collision accidents and reported near mid-air collision incidents occur in good visual FLite rules, VFR, weather conditions and during the hours of daylight. Most of these accidents/incidents occur within 5 miles of an airport and or near navigation aids. The see and avoid concept relies on knowledge of the limitations of the human eye, and the use of proper visual scanning techniques to help compensate for these limitations. The importance of, and the proper techniques for, visual scanning should be taught to a student pilot at the very beginning of FLite training. The competent FLite instructor should be familiar with the visual scanning and collision avoidance information contained in Advisory Circular, AC 90-48, Pilot's Role in Collision Avoidance, and the Aeronautical Information Manual, AIM. It should be noted that any turn or maneuver must be cleared before initiating. This is a most important concept in flying any aircraft. Look and clear the area of any aircraft or obstructions before any maneuver is performed. As an example, if a right-hand turn is to be performed, the pilot must look right and clear the area before initiating any turn to the right. This clearing procedure must be done before performing any maneuver. This is an important habit for any student for safety purposes and is incorporated into the pilot certificate process. The pilot must be trained by a CFI in effectively clearing the area before any maneuver is performed. There are many different types of clearing procedures. Most are centered around the use of clearing turns. Some pilot training programs have hard and fast rules, such as requiring 2 90-degree turns in opposite directions before executing any training maneuver. Other types of clearing procedures may be developed by individual FLite instructors. Whatever the preferred method, the FLite instructor should teach the beginning student an effective clearing procedure and require its use. The student pilot should execute the appropriate clearing procedure before all turns and before executing any training maneuver. Proper clearing procedures, combined with proper visual scanning techniques, are the most effective strategy for collision avoidance. Runway incursion avoidance. A runway incursion is any occurrence at an airport involving an aircraft, vehicle, person, or object on the ground that creates a collision hazard or results in a loss of separation with an aircraft taking off, landing, or intending to land. The 3 major areas contributing to runway incursions are communications, airport knowledge, and flight deck procedures for maintaining orientation. Taxi operations require constant vigilance by the pilot and can be assisted by the passenger. This is especially true during FLite training operations. Both the student pilot and the FLite instructor need to be continually aware of the movement and location of other aircraft and ground vehicles on the airport movement area. Many FLite training activities are conducted at non-towered airports. The absence of an operating airport control tower creates a need for increased vigilance on the part of pilots operating at those airports. Planning, Clear communications and enhanced situational awareness during airport surface operations will reduce the potential for surface incidents. Safe aircraft operations can be accomplished and incidents eliminated if the pilot is properly trained from the outset and, throughout his or her Ying career, accomplishes standard taxi operating procedures and practices. This requires the development of the formalized teaching of safe operating practices during taxi operations. Positive transfer of controls during flight training. There must always be a clear understanding between the student and FLIght instructor of who has control of the aircraft. Prior to any dual training FLIght, the instructor should conduct a brief ENG that includes the procedure for the exchange of flight controls. The following 3-step process for the exchange of flight controls is highly recommended. When a FLIght instructor wishes the student to take control of the aircraft, he or she should say to the student, "You have the FLIght controls." The student should acknowledge immediately by saying, "I have the FLIght controls." The FLIght instructor confirms RMS by again saying, "You have the FLIght controls." Part of the procedure should be a visual check to ensure that the other person actually has the FLIght controls. When returning the controls to the FLIght instructor, the student should follow the same procedure the instructor used when giving control to the student. The student should stay on the controls until the instructor says, "I have the FLIght controls." There should never be any doubt regarding who is flying the WSC aircraft. Numerous accidents have occurred due to a lack of communication or misunderstanding regarding who actually had control of the aircraft, particularly between student and FLIght instructor. Establishing the positive transfer of controls procedure during initial training will ensure the formation of a very beneficial habit pattern. Aeronautical decision-making, ADM, a PIC's attitude or mindset must always be alert in order to maintain the safety of the aircraft, passengers, and the general public on the ground. To accomplish sound aeronautical decision-making, ADM, a pilot must be aware of his or her limitations and well-being, physical and psychological health, even before beginning the faa-h-8083-5 pre-flight routine. While technology is constantly improving equipment and strengthening materials, safe flight comes down to the decisions made by the human pilot prior to and during FLIght. The well-being of the pilot is the starting point for the decision-making process that occurs while in control of the aircraft. Just as physical fatigue and illness directly affects a pilot's judgment, so too will attitude management, stress management, risk management, personality tendencies, and situational awareness. Hence, it is the awareness of human factors and the knowledge of the related corrective action that not only improves the safety of operating a WSC aircraft, but also enhances the joy of flying. Figure 118, a good starting point is the Pilot's Handbook of Aeronautical Knowledge, faa-h-8083-5, which explains the decision-making process, resource management, situational awareness, pilot error, stress management, risk management techniques, and hazardous attitude antidotes. After reading and understanding those subjects, it should be understood that the scenarios presented are generally for more complex airplanes, but the thought process and results are the same for all aircraft. The information is not duplicated, but the differences and additional information specific to WSC is provided in subsequent sections. The differences in the more complex airplane requirement scenarios presented in the Pilot's Handbook of Aeronautical Knowledge versus WSC aircraft characteristics can easily be compared. Overall, the advantage of an LSA is the simpler design requiring less pilot attention than the complex requirements of more complicated designs that add to the pilot's workload, such as constant speed propellers, multiple engines, retractable landing gears, faster air speeds. The unique characteristics on the WSC aircraft that increase ADM tasks are open FLIght deck where maps or other materials cannot be opened, shown, and discussed with passenger. Pusher propeller in the back, through which any loose item on the FLIght deck can be pulled, possibly producing severe damage, depending on the size of the object. More physical strength and endurance required to fly in turbulent conditions, which adds an additional risk element. Avoiding pilot errors. Overall, WSC aircraft are flown for fun and not for transportation. Generally, it is determined that the pilot will not fly in instrument meteorological conditions, IMC, without the assistance and training of the attitude indicator. Pilots must make the decision to stay out of IMC conditions and turn back immediately if the situation occurs. This is what most pilots should do, but the information provided by the attitude indicator allows pilots to start the error chain that can lead to catastrophic consequences. The best immediate decision is always to turn back and not go into IMC conditions in a WSC aircraft. With an open FLIght deck, the problem of items getting loose and hitting the propeller requires extra caution. Being in a hurry, not making sure everything is secured, and forgetting to brief the passenger can trigger one event that leads to another. Exercising caution in the open FLI deck is an important step for WSC pilots. If ying a WSC aircraft in turbulence, the pilot must have both hands on the bar to maintain control of the aircraft. Therefore, changing radio frequencies, measuring courses on the map, or operating any of the FLI deck controls becomes difficult and secondary to maintaining control of the aircraft. This is different from ying an airplane or a powered parachute, which requires less physical effort to maintain control of the aircraft, and at least one hand is available to tend to FLI deck duties. It must be noted that the faa-h-8083-5 priority always is maintaining control of the aircraft, and all other duties are secondary. Generally, pre-flight planning and good pilot judgment would prevent a situation of ying in moderate to extreme turbulence. However, when you do faa-nd yourself ying in this situation, fly the aircraft faa-ht, and attend to FLI deck duties second. Scenario-based training: a good instructor immediately begins teaching ADM when the student has the ability to control the WSC aircraft confidently during the most basic maneuvers. The instructor incorporates scenario-based training in which the instructor provides pilot, aircraft, environment, and operational risk elements to train the student to utilize ADM in making the best decision for a given set of circumstances. During a profi-sciency or practical test, the instructor or examiner evaluates the applicant's ability to use satisfactory ADM practices as the pilot determines risks and coordinates safe procedures. Resource management is similar to that described in the Pilot's Handbook of Aeronautical Knowledge, faa-h-8083-5, except the passenger cannot help in the same ways as in an airplane. The passenger cannot hold or help read the map unless the pilot has provided a knee board or other means for the passenger to assist. Figure 119. In addition to having the passenger scan the skies for other aircraft, the passenger can maintain control of the aircraft for short periods as the WSC is relatively easy to fly straight. This permits the pilot to perform unanticipated flight deck functions during FLI. Overall, pre-flight planning and passenger brief ENGS are additional tasks of resource management for the WSC aircraft. Use of checklists. Checklists have been the foundation of pilot standardization and FLI deck safety for many years and the faa-ht defense against the error chain that leads to accidents. Figure 120. The checklist is an aid to the fallible human memory and helps to ensure that critical safety items are not overlooked or forgotten. However, checklists are of no value if the pilot is not committed to their use. Without discipline and dedication in using a checklist, the odds favor the possibility of an error. The importance of consistent use of checklists cannot be overstated in pilot training. A major objective in primary FLI training is to establish habitual patterns that will serve pilots well throughout their FLIing careers. The FLI instructor must promote a positive attitude toward the use of checklists, and the student pilot must recognize their importance. Because of the evolution of WSC aircraft and their simplicity, it could be thought that written checklists are not required. Nothing is further from the truth. Following good written checklists provides significant safety for human factors, which is the greatest cause of accidents in aviation. 5 important written checklists must be used before FLI. These specific checklists are emphasized because of their importance in avoiding pilot errors that can occur before or during FLI. 1. Pre-flight preparation. 2. Routine pre-flight inspection. 3. Passenger pre-flight brief. 4. Engine start/taxi. 5. Pre-flight check. Because checklists may not be practical in the open FLI deck during FLI, and depending on the manufacturer and make/model of the WSC aircraft, checklists used for climb, en route, and landing may be placards in the FLI deck that can be read by the pilot at FLI or used on kneeboards as appropriate. Checklists must be secured to prevent their FLIing through the propeller during taxi or FLI. An additional written checklist that can be used on the ground after landing is taxi, engine shutdown, post-flight inspection, and securing aircraft. Medical factors. A number of physiological effects can be linked to FLIing. Some are minor, while others are important enough to require special attention to ensure safety of FLI. In some cases, physiological factors can lead to in-flight emergencies. Some important medical factors that a WSC pilot should be aware of include hypoxia, hyperventilation, middle ear and sinus problems, spatial disorientation, motion sickness, carbon monoxide poisoning, stress and fatigue, dehydration, heat stroke, and hypothermia. Other factors include the effects of alcohol and drugs, and excess nitrogen in the blood after scuba diving. Fatigue. WSC aircraft moves weight through pilot input. There is significant arm and upper body strength required to FLY a WSC aircraft, especially in turbulence. If flying a cross-country flight midday in moderate turbulence for more than an hour, a pilot would require significant strength and endurance. This significantly adds to fatigue, as discussed in the pilot's Handbook of Aeronautical Knowledge. This is accomplished all the time by experienced pilots, but it is a workout. If this type of workout is combined with dehydration in a desert environment, a greater than anticipated headwind, or ying an unfamiliar cross-country route, the added aeromedical risk factors could lead to a fatal error chain. Hypothermia. Hypothermia is an important factor and knowledge requirement in the WSC practical test standards. Cold temperatures for long periods reduce the inner body core temperature when the heat produced by the body is less than the amount of heat being lost to the body's surroundings. This loss of heat is highly accelerated in WSC open ight decks with wind chill. The faa-h-8083-5 symptom of ying a WSC aircraft is cold hands because of exposure to wind chill. Symptoms continue with other parts of the body becoming cold until the entire body feels cold. Hypothermia results in weakness, shivering, lack of physical control, and slurred speech followed by unconsciousness and death. Dressing warm and aircraft heating systems to help the pilot remain warm during flight prevents hypothermia. Motorcycle gloves and socks that run off the aircraft electric system are commonly used and can keep a pilot from getting cold. Figure 121, also, carrying an appropriate survival kit. Prepares a pilot against hypothermia if forced down in cold temperatures. Medical summary. Before approaching the WSC aircraft, a pilot must take a moment to reflect upon current medical, physical, and psychological conditions. During this time, a pilot should evaluate his or her ability to conduct the flight considering self, passenger, and people and property on the ground. Using the safe checklist is a smart way to start a pre-flight before getting to the WSC aircraft. Prior to flight, assess overall fitness as well as the aircraft's airworthiness. Figure 122, Chapter Summary. This chapter provides basic knowledge that is essential for WSC pilots and should serve as a starting point for them. However, there are many other handbooks, advisories, and regulations with which all WSC pilots should become familiar as their maturity within the aeronautical realm increases, and/or the need for greater depth of understanding becomes necessary due to location, temperature, altitude, etc.